The universe is vast, mysterious, and brimming with secrets so profound that even the greatest scientific minds are left in awe. It is a realm where the rules of reality are tested, where light bends, time warps, and forces beyond our comprehension shape the very fabric of existence. For centuries, humanity has gazed into the night sky, driven by an insatiable curiosity to understand the cosmos. Yet, with all our advancements in technology and exploration, the universe continues to guard some of its most perplexing phenomena. In this video, we are venturing beyond the bounds of our imagination to explore 30 strange and mind-boggling mysteries of deep space that have defied explanation. From invisible forces pulling entire galaxies to objects that seem to defy the very laws of physics, each phenomenon offers a glimpse into the unknown. Join us on this journey to the farthest corners of the cosmos, where every discovery raises new questions and challenges the limits of what we think we know. Now turning to the first phenomenon, we encounter the enigmatic entity known as the Great Attractor. Hidden within the Laniakea supercluster, this gravitational anomaly exerts an immense pull on galaxies, including our own Milky Way, drawing them toward it at staggering speeds of millions of miles per hour. What makes the Great Attractor so mysterious is its location behind the zone of avoidance, a dense region obscured by the gas and dust of our galactic plane, rendering it nearly impossible to observe directly. Scientists have pieced together its existence using indirect evidence, such as the unusual movement of galaxies in its vicinity. While some theories suggest it could be a massive concentration of galaxies or even an unusually dense supercluster, the exact nature of this cosmic magnet remains unclear. It is a powerful reminder of how much we have yet to uncover about the forces shaping our universe, leaving experts deeply intrigued and eager to unravel its secrets. Moving forward, another phenomenon emerges to challenge our understanding of cosmic motion, one that might even point to unseen realms beyond the observable universe. As the next challenge unfolds, we delve into the perplexing phenomenon known as dark flow. This is no ordinary cosmic motion, but an enormous drift involving galaxy clusters moving uniformly in the same direction at speeds surpassing 1 million miles per hour. What sets this apart from typical galactic movement is how it defies the expected patterns predicted by our current understanding of the universe's expansion. Normally, galaxies should scatter uniformly in all directions due to the influence of dark energy. Yet dark flow reveals a distinct and unexplained movement to a specific area of the sky. What could possibly create such a pull? One leading hypothesis suggests it might be the gravitational influence of something beyond the observable universe, such as massive structures or even another universe altogether. This hints at scales of reality far larger than anything we can see or measure. Yet, the lack of direct evidence leaves much room for debate, with some experts proposing that dark flow could stem from fundamental forces we have yet to fully comprehend. Whatever its origin, this phenomenon challenges our very framework for understanding the cosmos and raises tantalizing questions about what might lie beyond the limits of human observation. Now, as we move further into the cosmos, a strange visitor to our solar system emerges, one that sparked intense speculation and debate among scientists worldwide. With the next phase of the journey in sight, we encounter Oumuamua, a truly enigmatic visitor that made history as the first known interstellar object to traverse our solar system. Discovered in 2017, Oumuamua immediately captured the attention of astronomers due to its peculiar characteristics. Unlike the rounded shapes typically associated with asteroids or comets, this object displayed an elongated, cigar-like form, measuring roughly 10 times longer than it was wide. But its shape was only the beginning of the mystery. As it moved away from the Sun, Oumuamua exhibited unusual acceleration, deviating slightly from the trajectory predicted by gravity alone. This anomaly sparked heated debates, with scientists scrambling to explain its behavior. Was this acceleration caused by the release of gas and dust as seen with comets, even though no such trail was detected, or could it be something far more extraordinary? Some researchers proposed that Oumuamua might be an advanced piece of alien technology, perhaps a solar sail designed to harness the energy of starlight for propulsion. Such theories, while speculative, highlight how little we truly know about interstellar travelers. To this day, the origins and nature of Oumuamua remain shrouded in mystery, leaving both mainstream and fringe scientists intrigued. Could it be a natural object from a distant star system, or might it represent evidence of intelligent life beyond our own? As the dust settles on this cosmic mystery, another signal from the depths of space beckons, carrying with it even more questions than answers. Now turning to an event that has captivated both scientists and enthusiasts for decades, we encounter the famous WOW signal, a moment in 1977 that still echoes through the corridors of cosmic mystery. Detected by the Big Ear radio telescope in the United States, this narrowband radio signal was unlike anything ever recorded before. It lasted a mere 72 seconds, but those few moments were enough to send shockwaves through the scientific community. The signal appeared to originate from the direction of the Sagittarius constellation, a region of the sky not linked to any known objects that could naturally produce such a broadcast. What truly set it apart was its strength and clarity, far surpassing the usual background noise of the cosmos. The astronomer who discovered it, Jerry Amon, was so astonished that he scrawled the word "WOW" on the printout, giving the signal its memorable name. Despite exhaustive attempts to detect the signal again, it has never been repeated, adding another layer to its enigmatic nature. Was this a one-off event from an unknown natural source, or could it have been a deliberate transmission from an advanced extraterrestrial civilization? While some skeptics argue it might have been caused by a man-made satellite or an undiscovered space phenomenon, no definitive explanation has ever emerged. The WOW signal remains one of the most compelling pieces of evidence in the search for intelligent life, reminding us just how little we understand about the whispers of the universe. Moving forward, another cosmic enigma awaits, one that arrives in bursts and disappears just as quickly, leaving behind an even greater puzzle. As the next challenge unfolds, we dive into the enigma of fast radio bursts, short but powerful flashes of radio waves originating from deep space. These bursts, lasting only a few milliseconds, are so intense that they release as much energy in that tiny fraction of time as the sun does in several days. First discovered in 2007, they have since become one of the most puzzling cosmic phenomena. What makes them even more intriguing is that some are one-time events, while others mysteriously repeat, coming from the same location across varying intervals. Scientists have found them scattered throughout the universe, yet their origins remain shrouded in uncertainty. One leading theory suggests they might be associated with magnetars, a type of neutron star with an incredibly strong magnetic field, capable of producing such energetic radio waves. Another perspective speculates they could be linked to phenomena we have yet to fully understand, including interactions between extreme cosmic objects. And then, there's the more speculative idea that some could be deliberately created by advanced alien civilizations, perhaps as interstellar beacons or signals. Despite advancements in technology and years of research, the true cause of fast radio bursts remains hidden in the depths of space, adding another layer of mystery to the universe's strange and captivating stories. Now, speaking of mysteries, let us journey to a place where emptiness itself becomes the puzzle, a region so vast and vacant that it challenges everything we thought we knew about the structure of the cosmos. Now turning to the enigmatic Boötes Void, a region of space so vast and empty that it has baffled astronomers since its discovery. Spanning an incredible 330 million light-years across, this cosmic void contains an unusually small number of galaxies, making it one of the most desolate places in the observable universe. To put its emptiness into perspective, most regions of space have galaxies scattered throughout, like grains of sand on a beach. Yet in the Boötes Void, there is an almost eerie absence. Scientists estimate that fewer than 60 galaxies reside in this gigantic expanse, whereas in a typical region of the same size, thousands of galaxies would be expected. The formation of such a massive void raises profound questions about the structure and evolution of the universe. How could such an extensive area remain so underpopulated by galaxies? Current models of cosmic formation suggest that gravitational forces should have drawn more matter into this region over billions of years, but the Boötes Void seems to defy these predictions. Some theories propose that smaller voids may have merged over time, creating this colossal gap, while others suggest that the early universe experienced conditions that somehow prevented galaxies from forming here in the first place. Its sheer size, combined with the immense distances between the few galaxies that do exist within it, makes it a challenge to study in detail. Even with modern technology, unlocking the secrets of the Boötes Void remains elusive. Its isolation and emptiness stand as a stark reminder of just how little we truly understand about the cosmos. And while this vast, silent expanse leaves us searching for answers, the mysteries of deep space continue to unfold. With that in mind, let us turn our attention to the curious case of a star whose strange, flickering light patterns could hint at something truly extraordinary. Now turning to the perplexing mystery of Tabby's star, a celestial object that has captured the imagination of scientists and the public alike. Officially named KSE 8462852, this star sits roughly 1,400 light-years away in the constellation Cygnus, and it exhibits behavior unlike anything we have ever seen. Its light undergoes irregular and significant dimming that cannot be fully explained by the usual suspects like orbiting planets or clouds of dust. What makes Tabby's star so intriguing is the sheer unpredictability of its dimming patterns. At times, its brightness drops by up to 20%, a staggering amount for a star of its type. To put this into perspective, a planet passing in front of a star usually causes a brightness drop of only about 1%. Theories attempting to decode this phenomenon are as varied as they are fascinating. Some scientists speculate that a massive swarm of comets, perhaps disrupted by a nearby stellar event, could be blocking the star's light intermittently. However, this idea struggles to account for the scale and randomness of the dimming events. Others suggest a more exotic explanation, an alien megastructure. This hypothetical construct, perhaps designed to harness the star's energy, could theoretically create the observed light fluctuations. While this idea is purely speculative, its allure has sparked widespread interest. Another possibility involves unusual stellar activity, where the star itself might be undergoing processes that we have yet to understand. Despite extensive observations, no single theory has been able to definitively solve the puzzle of Tabby's star. It remains a tantalizing reminder of how much we still have to learn about the cosmos. And as we ponder whether natural forces or something far more extraordinary are at play here, the next mystery on our journey takes us to the elusive concept of dark matter, a substance that may hold the key to understanding the very fabric of the universe. Now turning to the enigmatic concept of dark matter, we encounter a substance that makes up about 27% of the universe's total mass and energy, yet remains invisible and undetectable through conventional means. Unlike the matter we are familiar with, which absorbs, emits, or reflects light, dark matter interacts with the universe in a completely different way solely through gravity. Its elusive nature means it cannot be observed directly, but its presence is inferred through its profound gravitational effects on galaxies and cosmic structures. Without dark matter, the universe as we know it would not exist in its present form. For example, galaxies spin at such speeds that their stars should, theoretically, be flung out into the void of space. Yet something unseen provides the additional gravitational pull needed to hold them together, and that something is believed to be dark matter. It also plays a crucial role in the formation of large-scale cosmic structures. Observations show that galaxy clusters and superclusters align along vast, filament-like structures, often referred to as the cosmic web. Scientists theorize that dark matter acts as the scaffolding for these immense formations, guiding how normal matter coalesces under gravity to form stars and galaxies. Despite its crucial role in shaping the universe, dark matter remains one of the greatest puzzles in modern science. Researchers have developed a range of theories to explain its composition, from unknown particles that interact weakly with other matter to more exotic ideas involving parallel universes or modifications of gravitational laws. Efforts to detect dark matter using vast underground detectors or high-energy particle colliders have so far yielded no definitive results, heightening the mystery. As we grapple with questions about what this invisible substance truly is and how it fits into the grand cosmic puzzle, it challenges our very understanding of physics and the universe's inner workings. And with this mystery still unsolved, our journey into the unknown deepens further as we confront an even more perplexing force: dark energy, the enigmatic phenomenon driving the accelerating expansion of the cosmos. Moving forward, we encounter an even more baffling force: dark energy, a mysterious phenomenon that accounts for an astonishing 68% of the universe. Unlike dark matter, which exerts a gravitational pull, dark energy seems to work against gravity, pushing the fabric of space itself apart. Its existence was first hinted at in the late 1990s when astronomers observed that distant supernovae were dimmer than expected. A discovery that indicated the universe's expansion is not slowing down as previously thought, but is instead accelerating. This startling revelation turned our understanding of cosmology on its head. Current theories suggest that dark energy could be tied to the inherent energy of empty space, often referred to as the cosmological constant, or it might be a new dynamic field influencing the universe on vast scales. However, both interpretations come with challenges that defy existing physics. The cosmological constant, for instance, raises perplexing questions about why its value is so small yet not zero, while dynamic field theories require the existence of entirely new physics. The influence of dark energy is most evident on the largest scales of the cosmos, shaping the evolution of galaxies, galaxy clusters, and the cosmic web itself. Without dark energy, the universe might have collapsed back in on itself or expanded much more slowly, never allowing the formation of the intricate structures we see today. Yet despite its monumental impact, no direct detection of dark energy has been achieved, leaving scientists reliant on indirect observations and theoretical models. This conundrum not only challenges our understanding of the universe, but also exposes the limits of our scientific knowledge, pushing researchers to rethink fundamental concepts in physics. As we ponder the immense influence of dark energy, it is clear that its secrets remain one of the greatest enigmas in our quest to comprehend the cosmos. With its mysteries leaving us humbled and inspired, we now turn our focus to a peculiar phenomenon much closer to home: the unexplained gamma-ray emissions at the center of our very own Milky Way galaxy. Now turning to the heart of our own galaxy, we encounter the mysterious excess of gamma-ray emissions at the center of the Milky Way, a phenomenon that has confounded scientists for years. Gamma rays, the most energetic form of light, are not uncommon in the universe, often produced by violent events like supernova or the activity of black holes. However, the gamma-ray glow observed at the galactic center stands out because its intensity cannot be fully explained by known sources. This anomaly, sometimes referred to as the galactic center gamma-ray excess, has sparked a wide array of theories. One compelling explanation suggests that these gamma rays could be the result of dark matter particles annihilating each other. If true, this would provide groundbreaking evidence for the existence and nature of dark matter, potentially unlocking secrets about this elusive substance that makes up a significant portion of the universe. Alternatively, some scientists propose that the emissions could arise from a population of rapidly spinning neutron stars known as pulsars densely packed in the region. These pulsars could produce gamma rays as they emit beams of radiation while spinning at incredible speeds. Yet another hypothesis points to previously unknown astrophysical phenomena or interactions within the extreme environment around the supermassive black hole at the center of our galaxy. Despite years of research and advanced observations, none of these theories have been conclusively proven, leaving this gamma ray glow shrouded in uncertainty. What adds to the intrigue is the fact that the galactic center is one of the most difficult regions to study, obscured by dense clouds of gas and dust, making direct observations challenging. This mystery not only deepens our fascination with the Milky Way, but also highlights how much we still have to learn about the forces and objects shaping our universe. With the lingering questions surrounding the galactic center gamma ray mystery, we now turn our attention to an equally enigmatic structure, a truly rare phenomenon known as Hoag's object, a galaxy that defies traditional classification. Now turning to one of the most visually striking and mysterious galaxies ever discovered, we arrive at Hoag's object. At first glance, this celestial marvel looks almost like a cosmic optical illusion. It consists of a nearly perfect ring of bright, young stars encircling an older, reddish core with an empty gap of space in between. This rare structure has baffled astronomers since its discovery in the 1950s. Unlike most galaxies, which fall into familiar shapes like spirals, ellipses, or irregular clusters, Hoag's object defies these traditional classifications. Its symmetry and composition raise profound questions about how such a unique configuration could have formed. One theory suggests that the galaxy may have emerged from a dramatic collision billions of years ago, where a smaller galaxy passed through a larger one, leaving behind the distinctive ring structure. Yet, detailed observations have found no sign of a secondary galaxy nearby, casting doubt on this explanation. Another hypothesis speculates that the ring could have formed through internal processes, such as gravitational instability, where material from the galaxy's core was somehow ejected and later coalesced into a circular orbit. However, this too leaves scientists puzzled, as such processes are rarely observed and poorly understood. Hoag's object becomes even more intriguing when considering how rare it is. While other ring galaxies have been found, none exhibit the same level of symmetry and isolation, making it a one-of-a-kind phenomenon in the known universe. Some even wonder if its formation could involve entirely unknown mechanisms or phenomena not yet accounted for in our current models of galaxy formation. To add to the mystery, astronomers have discovered another faint ring-like structure surrounding the galaxy, further complicating our understanding of its origin. Hoag's object is not just a visual spectacle, but also a reminder of how much remains unknown about the forces that shape galaxies. Its existence challenges our understanding and invites us to keep searching for answers. As we ponder the mysteries of this cosmic enigma, our journey continues to other strange phenomena, beginning with rogue planets, worlds that wander across the galaxy without a star to call home. Moving forward, we encounter an extraordinary cosmic mystery: rogue planets. Unlike the familiar planets in our solar system that orbit a star, rogue planets are free-floating wanderers drifting through the galaxy without a star to anchor them. These lonely worlds are not tethered by the gravitational pull of any stellar companion, making them some of the most elusive objects in the universe. The discovery of these planets has revolutionized our understanding of planetary systems. Scientists estimate that there could be billions or even trillions of rogue planets in our galaxy alone, far outnumbering the stars themselves. But how do such planets form, and how did they end up on their solitary journeys? One theory suggests that they might have originally formed around a star, just like traditional planets, but were violently ejected from their systems due to gravitational interactions or collisions. Another possibility is that rogue planets could form in isolation, directly from the collapse of a gas cloud, similar to how stars form, but on a much smaller scale. Both scenarios challenge our conventional ideas about the processes that shape planetary systems. These wandering worlds are particularly difficult to detect because they lack the light of a nearby star to illuminate them. Most discoveries come from a technique known as gravitational microlensing, where the planet's gravity briefly bends light from a distant star as it passes in front of it. Despite their elusive nature, rogue planets could hold vital clues about the history and evolution of galaxies. Some might even possess atmospheres, water, or other conditions that could theoretically support life, raising questions about the potential for habitability in the most unexpected places. The study of rogue planets forces us to rethink what we know about the formation, distribution, and diversity of planetary systems, making them one of the most fascinating and mysterious phenomena in the cosmos. As we marvel at these solitary wanderers, we now turn our attention to another galactic puzzle, the cannibalistic nature of the Andromeda Galaxy, and the clues it provides about the evolution of galaxies over time. As the next challenge unfolds, we come face to face with the phenomenon of galactic cannibalism within the Andromeda Galaxy. Unlike the serene image often associated with galaxies, Andromeda reveals a more turbulent side of the cosmos. It is devouring smaller neighboring galaxies, merging their stars, gas, and dark matter into its own colossal structure. This process, aptly referred to as galactic cannibalism, has been observed through streams of stars, remnants of devoured galaxies, that stretch out like cosmic scars across Andromeda's outskirts. These stellar streams act as a roadmap, providing crucial evidence of its violent appetite. Scientists believe that Andromeda's hunger for smaller galaxies is driven by gravity, as its massive size exerts an irresistible pull on its less massive neighbors. As these smaller galaxies are drawn in, their structures are ripped apart, and their components are seamlessly integrated into Andromeda's growing form. However, this process is not just about destruction, it also drives creation. As gas from the engulfed galaxies interacts with Andromeda's own, it can trigger bursts of star formation, breathing new life into the galaxy. What makes this phenomenon even more fascinating is its implication for our own Milky Way galaxy's future. Andromeda is on a collision course with the Milky Way in roughly 4 billion years, a cosmic event that will likely result in another round of galactic cannibalism on an unprecedented scale. The two galaxies will merge to form a new, larger galaxy, reshaping the local universe as we know it. Despite our growing understanding, many mysteries remain. Why do some galaxies like Andromeda engage in such aggressive behavior while others do not? And how exactly do these collisions influence the long-term evolution of galaxies? By studying Andromeda's current behavior, scientists hope to unlock clues about the lives and fates of galaxies across the universe. With this dramatic celestial dance in mind, we now shift our focus to another enigma centered around the heart of our Milky Way giant, X-ray, emitting bubbles that defy conventional explanations. As the next phenomenon emerges, we zoom in on the very heart of our Milky Way galaxy to uncover the mystery of the Fermi bubbles, gigantic structures extending tens of thousands of light years above and below the galactic center. These colossal formations, first revealed through X-ray and gamma-ray observations, seem to defy our conventional understanding of astrophysical processes. What exactly created these bubbles? That question remains one of the most perplexing puzzles in modern astronomy. Some scientists propose that they might be remnants of a colossal eruption from the supermassive black hole at the Milky Way's core, a relic from a time when it was far more active, spewing out immense amounts of energy. Others theorize that these structures could have formed from a burst of rapid star formation, where winds from newborn stars and supernova combine their power to carve out these enormous cavities. What makes the Fermi bubbles even more intriguing is their sharp edges, which suggest that the events creating them were sudden and immensely powerful. These bubbles aren't just empty voids, they emit high-energy radiation, challenging researchers to understand the processes fueling such emissions. Despite the wealth of data collected so far, no single explanation fully accounts for all their properties, leaving the scientific community with more questions than answers. Are similar phenomena present in other galaxies? If so, what does that say about the life cycles of galaxies and the role of black holes? As we ponder these towering cosmic enigmas, our journey takes an intriguing turn toward a chilling anomaly, the cold spot, a peculiar region in the background radiation of the universe that defies explanation. With the next phase of the journey in sight, let us unravel the mystery of the cold spot, a baffling anomaly nestled within the cosmic microwave background radiation, often regarded as the faint afterglow of the universe's birth. This peculiar region appears significantly cooler than its surrounding areas, a characteristic that challenges the very foundations of our cosmological models. According to the widely accepted theory of the Big Bang, variations in the cosmic microwave background radiation should be relatively minor, yet the cold spot stands out as an enigmatic exception. So, what could explain this strange phenomenon? One prevailing hypothesis suggests the existence of a supervoid, an immense region of space containing far fewer galaxies than expected. Such a void, stretching across billions of light years, could create an optical illusion of coolness as light passing through it loses energy, a process known as the integrated Sachs-Wolf effect. However, even this explanation struggles to fully account for the sheer scale and intensity of the cold spot. Other scientists propose a far more mind-bending theory. Perhaps this anomaly is evidence of a collision between our universe and another in a hypothetical multiverse. If true, this would hint at a reality far more complex than we can currently comprehend, one where universes ripple and interact like drops of water on a cosmic scale. And yet, these ideas, as tantalizing as they are, remain unproven, leaving the cold spot as an open question in the story of the cosmos. Could it be an unknown artifact of the early universe's formation, or is it a clue pointing us toward an even greater cosmic mystery? While this frigid enigma keeps scientists speculating, our cosmic expedition presses on, drawing us toward one of the oldest stars ever discovered, a relic that seems to predate the universe itself. Now turning to the Methuselah star, we encounter a celestial object that seems to defy the very fabric of our understanding of time and the universe. Officially catalogued as HD 140283, this star is located roughly 200 light-years away in the constellation Libra, and what makes it extraordinary is its estimated age. Initial calculations placed its age at approximately 14.5 billion years, an astonishing figure given that the universe itself is believed to be around 13.8 billion years old. This apparent paradox has left scientists grappling with questions that challenge the foundation of cosmological models. How could a star exist before the universe itself? Some suggest that the age discrepancy may stem from uncertainties in the methods used to measure both the age of the star and the age of the universe. Stars like Methuselah are often dated using their chemical composition and luminosity, but even slight errors in these measurements can lead to significant discrepancies. For instance, Methuselah's low metal content indicates it formed in the early stages of the universe, long before heavier elements were widespread. This aligns with its ancient nature but doesn't fully resolve the age anomaly. Others posit that the discrepancy might arise from unknown astrophysical processes or even inaccuracies in our understanding of the universe's expansion rate. Could this star be pointing to gaps in our knowledge, or is it merely a statistical anomaly? While researchers continue to refine their measurements and theories, the Methuselah star serves as a humbling reminder of how much we still have to learn about the cosmos. As we ponder the mysteries of this ancient star, we turn our gaze to another set of enigmatic objects, neutron stars with magnetic fields so extreme they defy comprehension. Moving forward, we encounter magnetars, an extraordinary and mysterious type of neutron star that represents the pinnacle of cosmic extremes. These are the remnants of massive stars that have undergone supernova explosions, leaving behind incredibly dense cores with some of the most intense magnetic fields in the known universe. To put their power into perspective, the magnetic field of a magnetar is over a quadrillion times stronger than the Earth's magnetic field. Such strength has mind-boggling effects on the surrounding space, including the ability to distort atoms and disrupt molecular bonds. Magnetars are also notorious for their unpredictable behavior. They often emit sudden bursts of high-energy radiation, such as gamma rays and X-rays, in events so powerful that they can be detected from millions of light-years away. One such event, recorded in the year 2004, came from a magnetar in our galaxy, and the resulting energy release was so immense that it temporarily disrupted Earth's ionosphere. Despite these insights, magnetars remain an enigma. Scientists are still working to understand how they form such extreme fields and why their emissions are sporadic. Some theories suggest that their magnetic fields arise from rapid spinning during their formation, while others point to phenomena we have yet to fully comprehend. Even their lifespan adds to the mystery as their magnetic fields decay over time, raising questions about how long they can remain active. As we uncover more about these astonishing objects, magnetars continue to serve as a vivid reminder of the universe's power and unpredictability. And with that awe-inspiring thought, we shift our focus to another cosmic mystery, the elusive missing baryons that challenge our understanding of the universe's matter. Now turning to the mysterious case of the missing baryons, we delve into a cosmic puzzle that has perplexed scientists for decades. Baryons are particles like protons and neutrons which make up ordinary matter, the kind that forms stars, planets, and even us. Astonishingly, only about half of the baryonic matter predicted by cosmological models has been directly observed in the universe. This means that the whereabouts of the remaining half has been one of astronomy's most profound mysteries. Over the years, scientists have proposed that these missing baryons might be hiding in vast, diffuse structures called the warm-hot intergalactic medium, a network of gas that exists between galaxies and is difficult to detect. Recent discoveries have provided tantalizing clues. Observations using space telescopes and radio surveys suggest that traces of this elusive matter can be found scattered as faint filaments of gas stretching across the cosmic web. Some studies even point to baryons being embedded within halos of hot gas that surround galaxies, invisible to most traditional detection methods. Nonetheless, confirming these findings remains a challenge. The sheer scale of the universe and the limitations of current technology make it incredibly difficult to map this faint, diffuse matter with certainty. Even with modern advancements such as the use of fast radio bursts to probe intergalactic space, concrete evidence of the missing baryons is elusive. Why this gap in our understanding persists is as intriguing as the problem itself. Could it be that our models of the universe need refinement, or are there yet undiscovered phenomena at play? The search for the missing baryons is not just about finding particles, it's about uncovering the fabric of the universe itself. And as this cosmic investigation unfolds, we turn our attention to another captivating enigma: hypervelocity stars, celestial objects that defy the boundaries of speed and challenge our understanding of motion in the cosmos. Now turning to hypervelocity stars, we explore a phenomenon that truly stretches the bounds of astrophysical understanding. These extraordinary stars have been ejected from their home galaxies at breakneck speeds, often exceeding escape velocity, which means they are fast enough to break free from their galaxy's gravitational pull entirely. Imagine a star traveling at over 1 million miles per hour, hurtling through intergalactic space. This is the astonishing reality of hypervelocity stars. But what could possibly accelerate such massive objects to these staggering speeds? Scientists believe that the most likely culprit is the interaction with supermassive black holes. When a binary star system ventures too close to a black hole, one of the stars can get captured by the immense gravitational force, while the other is flung away with incredible velocity like a cosmic slingshot. Another possible cause could be gravitational interactions during galactic mergers, where the chaotic dance of colliding stars and galaxies might propel some stars into interstellar exile. What makes hypervelocity stars so intriguing is not just their speed, but the profound implications they carry for our understanding of galactic dynamics and the forces shaping the universe. These runaway stars act as messengers, carrying with them traces of their origins and offering clues about the environments they were ejected from. At the same time, their trajectories provide a unique lens through which to study the gravitational landscape of the universe. Tracking their paths could even help map the distribution of dark matter, the invisible substance that influences the motion of galaxies. However, identifying these speedy travelers is no easy task. Their rarity and extreme distances make them hard to detect, often requiring precision measurements from advanced instruments like space telescopes. Yet, each discovery adds another piece to the puzzle of how these celestial outliers fit into the grand tapestry of the cosmos. As we marvel at the mystery of hypervelocity stars racing through the void, we shift our gaze to another astonishing feature within our very own solar system, Saturn's enigmatic hexagon, a geometric wonder that continues to baffle scientists and redefine what we know about planetary atmospheres. Now turning to Saturn's enigmatic hexagon, we encounter a phenomenon so unique that it defies expectations and inspires endless curiosity. Located at Saturn's north pole, this six-sided cloud pattern is a near-perfect geometric figure, spanning over 18,000 miles in diameter. To put that into perspective, it is large enough to fit 4 Earths side by side. First observed by the Voyager spacecraft in the early 1980s and later studied in greater detail by the Cassini mission, this mysterious structure has puzzled scientists for decades. What makes it even more intriguing is its remarkable stability. It has persisted for at least 40 years and possibly much longer without losing its sharp hexagonal shape. But what could possibly create and sustain such a precise and massive feature in a planet's atmosphere? One leading theory suggests that the hexagon is a result of a standing wave pattern in Saturn's fast-moving jet streams. Similar to how swirling water forms shapes in certain conditions, the interaction of atmospheric currents at different speeds and altitudes might generate the hexagon's symmetrical edges. Another hypothesis points to temperature variations in Saturn's upper atmosphere, where the polar vortex creates conditions conducive to maintaining this unique structure. Yet none of these explanations can fully account for the phenomenon's longevity or its perfect geometry. Adding to the mystery, the interior of the hexagon displays a kaleidoscope of flowing clouds, with changes in color and composition that shift with Saturn's seasons. Some scientists even speculate that the hexagon may extend deeper into Saturn's atmosphere than previously assumed, potentially revealing new dynamics at work within the planet. This bizarre feature challenges our understanding of fluid dynamics, planetary atmospheres, and even the fundamental principles that govern weather patterns on other worlds. While research continues, the hexagon serves as a reminder of how little we truly know about the forces shaping the planets in our own cosmic backyard. As we leave behind the mysteries swirling within Saturn's atmosphere, we turn our attention to objects even more luminous and powerful: quasars, the distant beacons that illuminate the far reaches of the universe with astonishing energy. Now turning to quasars, we encounter some of the most powerful and luminous objects in the universe, capable of outshining entire galaxies. These extraordinary phenomena are powered by supermassive black holes located at the centers of distant galaxies. As matter spirals into these black holes, it forms an accretion disk, a swirling mass of gas and dust heated to extreme temperatures. This process releases an incredible amount of energy, ejecting light that travels across billions of light years to reach us. What makes quasars particularly valuable to scientists is that they act as natural cosmic lighthouses, illuminating the farthest corners of the universe and offering insights into its early stages. Studying their light allows astronomers to peer back in time, unraveling details about conditions in the young universe. However, quasars are far from fully understood. Their immense energy output raises questions about how supermassive black holes can sustain such activity over long periods. Adding to the mystery is their variability. Quasars can dim or brighten unexpectedly over time, and the reasons behind these changes are not entirely clear. Some scientists believe that the variations could be linked to disruptions in the flow of matter into the black hole, while others point to interactions with nearby stars or galaxies. Moreover, the role of quasars in galaxy formation and evolution remains a profound puzzle. Observations suggest that the immense energy released by a quasar can influence the surrounding environment, potentially suppressing or triggering star formation in nearby regions. Yet the mechanisms behind these interactions are not well understood, leaving gaps in our knowledge about how quasars shape the structure and behavior of galaxies. In addition, most quasars are located at immense distances from Earth, which adds to the difficulty of studying them. Despite this, advancements in telescopes and imaging technology have begun to shed new light on these enigmatic objects. Still, the questions surrounding their origins, behavior, and impact on the universe ensure that quasars remain one of the most fascinating and perplexing topics in astronomy. As we continue our exploration, we move from these dazzling cosmic beacons to examine the strange effects of gravity and time near the universe's most mysterious giants, black holes. As the next challenge unfolds, we delve into one of the most mind-bending phenomena in the universe: time dilation events near black holes. Black holes are regions of space where gravity is so intense that not even light can escape their pull. This extreme gravitational force also has a profound effect on time itself, as predicted by Albert Einstein's theory of general relativity. Near a black hole, the fabric of space-time stretches and curves, causing time to slow down dramatically for anyone close to its event horizon, the boundary beyond which nothing can return. For an observer farther away, time appears to move at its normal pace, but for someone closer to the black hole, seconds can feel like hours or even years, depending on the black hole's mass and proximity. This phenomenon has been confirmed by observing the faint ripples in space-time known as gravitational waves, which are produced when massive objects like black holes collide or interact. The groundbreaking detection of these waves has allowed scientists to directly measure time dilation in extreme cosmic events. For instance, during the merger of two black holes, the intense warping of space-time causes time to behave in ways that defy ordinary comprehension. These detections have not only confirmed key aspects of relativity, but have also raised new questions about the boundaries of physics. One of the most fascinating implications of time dilation near black holes is its potential for exploring the nature of the universe itself. Some theories suggest that the intense stretching of space-time could provide clues about the fundamental structure of reality, possibly revealing hidden dimensions or deeper laws of physics that connect gravity and quantum mechanics. However, studying these effects comes with significant challenges. Black holes, by their very nature, are difficult to observe directly, and much of what we know comes from indirect measurements like the gravitational waves mentioned earlier. For now, the mysteries of time dilation near black holes continue to fuel the imagination of scientists and space enthusiasts alike. And as technology advances, we may one day unlock the secrets of these enigmatic giants and their ability to bend not just space but time itself. Transitioning from these gravitational marvels, we move to another vast and puzzling feature of the universe, the Eridanus supervoid. Now turning to the Eridanus supervoid, we encounter a vast and perplexing region of space that has left scientists searching for answers. The Eridanus supervoid is an enormous, nearly empty area spanning over 1 billion light-years in diameter. What makes it especially intriguing is its connection to the cold spot, a mysterious anomaly in the cosmic microwave background radiation, the faint glow left over from the birth of the universe. This cold spot appears noticeably colder than the surrounding regions of the sky, and the presence of the Eridanus supervoid overlapping with it has raised compelling questions. How could such a massive emptiness form in a universe that is otherwise teeming with galaxies, stars, and cosmic matter? One theory suggests that this supervoid might be the result of quantum fluctuations that occurred shortly after the Big Bang, creating pockets of lower density where matter failed to accumulate. Another hypothesis explores the idea that the void could be indicative of something even more extraordinary, such as evidence of interaction with another universe. Some cosmologists propose that the cold spot and the Eridanus supervoid might hint at a collision between our universe and a parallel one, causing unusual distortions in the cosmic microwave background. While these ideas remain speculative, they underscore the potential for the Eridanus supervoid to reshape our understanding of the cosmos. Interestingly, the supervoid may also have implications for the large-scale structure of the universe. Massive voids like this one can influence the motion of nearby galaxies and even distort light traveling through them, leading to phenomena like gravitational lensing. By studying these effects, scientists hope to gain deeper insights into the distribution of matter throughout the universe and the forces shaping it. However, confirming these theories is no easy task. Observing and measuring such an immense, underdense region comes with significant challenges, as the distance and scale are almost incomprehensible. Even so, advancements in astronomical tools and simulations are steadily bringing us closer to answers. For now, the Eridanus supervoid remains one of the most enigmatic features of the cosmos, a reminder of how much we have yet to uncover about the universe's intricate tapestry. With our focus set on unraveling these vast cosmic mysteries, we next delve into another fascinating concept that pushes the boundaries of theoretical physics, cosmic strings. Moving forward, we encounter the intriguing concept of cosmic strings, hypothetical structures that could hold the keys to understanding the very fabric of our universe. These cosmic strings are theorized to be incredibly thin, yet immensely dense, defects in space-time that may have formed during the early stages of the universe. Imagine them as cosmic threads stretching vast distances across the universe, potentially millions of light-years long, yet thinner than an atom. Their existence arises from the idea that as the universe cooled after the Big Bang, phase transitions similar to those in materials like metals and magnets might have occurred, leaving behind these unique imperfections in space-time. What makes cosmic strings so fascinating is their potential to explain some of the great mysteries of deep space. For instance, their immense gravitational pull could distort space-time to such an extent that they act as lenses, bending light from distant galaxies and creating observable effects that astronomers might detect. This phenomenon, known as gravitational lensing, could provide evidence of their presence and offer clues about their properties. Additionally, cosmic strings are thought to generate powerful ripples in space-time, known as gravitational waves. These waves, if detected, could offer a new way to study the early universe and confirm the existence of these elusive structures. Some scientists speculate that cosmic strings might be connected to the formation of galaxies and large-scale structures in the universe, acting as cosmic scaffolding that guided the distribution of matter. However, despite decades of theoretical work and advancements in technology, concrete observational evidence for cosmic strings remains elusive. Their theoretical nature, combined with the profound implications of their existence, makes them a subject of intense debate and fascination. Detecting cosmic strings would not only confirm a long-standing prediction in theoretical physics, but could also open up an entirely new dimension of understanding about the origins and evolution of the universe. As scientists continue to refine gravitational wave detectors and analyze vast amounts of astronomical data, the search for these cosmic threads marches on. Whether or not we ever uncover definitive evidence of cosmic strings, their allure lies in the possibilities they represent, a bridge between the known and the unknown, the visible and the hidden. From this captivating theoretical puzzle, we now turn our attention to a more tangible mystery that directly challenges our understanding of galactic formation, the missing satellites problem. Now turning to the perplexing mystery of the missing satellites problem, we delve into an enigma that directly challenges our understanding of galactic formation and the distribution of matter in the universe. According to prevailing theories, the Milky Way should be surrounded by hundreds, if not thousands, of small, faint galaxies known as dwarf galaxies. These diminutive companions, rich in dark matter, are thought to be leftover building blocks from the formation of larger galaxies. However, when astronomers set out to observe these predicted satellite galaxies, they uncovered a puzzling shortfall. Only a few dozen have been discovered, far fewer than theoretical models predict. This glaring discrepancy has sparked intense debate and prompted scientists to re-examine their models of how galaxies form and evolve. One possible explanation lies in the nature of dark matter itself. If dark matter behaves differently than current theories suggest, such as being warmer and more inclined to clump together, it could prevent the formation of smaller structures like dwarf galaxies. Another theory proposes that the missing galaxies do exist but are simply too faint or distant to detect with current technology. These ultra-faint galaxies, composed mostly of dark matter with very few stars, might be lurking on the edges of our observational capabilities. Alternatively, the answer might involve the violent history of the Milky Way's growth. As our galaxy consumed smaller galaxies, the gravitational and tidal forces may have stripped away their stars and gas, leaving behind remnants so dispersed that they no longer resemble dwarf galaxies. Still, other scientists speculate that energetic events such as supernova explosions could have ejected the gas needed for star formation in these small galaxies, effectively halting their growth before they could become visible. While efforts like advanced sky surveys and simulations have brought some clarity, the missing satellites problem remains unresolved. This paradox not only pushes astronomers to refine their theories, but also provides an exciting opportunity to advance our understanding of dark matter and the dynamics of galaxy formation. As tools like next-generation telescopes and more sensitive observation techniques come online, the hope is that these elusive companions of the Milky Way will finally reveal themselves. Whether their absence challenges the fundamentals of our cosmic models or their discovery transforms our understanding of the universe, the missing satellites problem represents a tantalizing puzzle that continues to intrigue. With this quandary in mind, let us now journey deeper into the cosmos to explore an extraordinary event that bridged light and gravity, an astrophysical phenomenon known as GRB 170817a. With the next phase of the journey in sight, we uncover an extraordinary cosmic event that marked a groundbreaking milestone in astronomy. GRB 170817a. This phenomenon, detected in the year 2017, was the first of its kind to provide both light and gravitational wave signals from a single source, an event that originated from the merger of two neutron stars. Neutron stars, the incredibly dense remnants of massive stars, collide with such colossal force that they produce ripples in the very fabric of space-time gravitational waves and unleash an intense burst of gamma rays. What makes GRB 170817 so revolutionary is that, for the first time, scientists were able to observe both of these cosmic messengers simultaneously. This dual detection confirmed years of theoretical work predicting that neutron star mergers are a major source of gravitational waves and gamma-ray bursts. It also provided a critical link to phenomena such as kilinovae, massive explosions that produce elements like gold and platinum. However, as with any milestone discovery, new questions quickly arose. The gamma-ray burst detected in GRB 170817 was unexpectedly weak compared to similar events, challenging existing models of how these bursts are emitted. Scientists have proposed various explanations, such as the possibility that the jet of gamma rays was not directed fully toward Earth, or that a dense cocoon of material surrounding the merger absorbed much of the energy. Further complicating matters, the behavior of the gravitational waves offered insights into the characteristics of neutron stars, including their size, density, and internal composition, but also raised uncertainties about the extreme physics at play in these catastrophic collisions. This unprecedented observation demonstrated the power of multi-messenger astronomy, where different types of signals, light, gravitational waves, and even neutrinos are combined to paint a more comprehensive picture of cosmic events. GRB 170817 showcased how much we can learn when multiple observatories and instruments work in unison, from space-based telescopes to ground-based gravitational wave detectors. While it answered many questions about the violent universe, it also left scientists with lingering mysteries about the nature of gamma-ray bursts and the environments in which neutron star mergers occur. As research continues and technology advances, GRB 170817 remains a shining example of how collaboration and innovation can bring us closer to unraveling the secrets of the universe. Moving forward, we turn our gaze to a phenomenon that challenges our understanding of galaxy formation, at its very core the enigmatic presence of supermassive black hole pairings. With the next phase of the journey in sight, we delve into the fascinating yet perplexing discovery of supermassive black hole pairings. These cosmic phenomena occur within merging galaxies, where two colossal black holes, each millions or even billions of times the mass of the Sun, find themselves locked in a gravitational dance. As galaxies collide and merge, their central black holes are drawn toward one another, gradually spiraling closer over millions of years. What makes these pairings so intriguing is the profound impact they have on their host galaxies and the fundamental questions they raise about the universe. Scientists have observed that when these black holes interact, they can trigger turbulent activity, such as intense star formation or the sudden ejection of gas and dust, reshaping entire galaxies. Yet, their exact behavior remains elusive. One of the most puzzling aspects of supermassive black hole pairings is how they eventually merge. Theoretical models suggest that as the black holes approach each other, they lose energy through gravitational wave emissions, which are ripples in space-time. However, at a certain point, this energy loss appears to stall, creating what is known as the final parsec problem. Essentially, the black holes seem to become stuck at a small distance apart, leaving scientists to wonder how, or if, they can ever fully combine. Some theories propose that interactions with surrounding stars, gas, or even other black holes may help close this gap, but definitive evidence remains elusive. Adding to the mystery, recent studies have revealed that paired supermassive black holes are more common than previously thought, with advanced telescopes detecting signs of these cosmic duos in distant galaxies. This raises questions about the role they play in galaxy evolution and whether their mergers could account for some of the most energetic events in the universe, such as the formation of ultra-powerful jets of material or the mysterious presence of dormant black holes in certain galaxies. The discovery of these pairings has not only expanded our understanding of black holes, but also challenged existing models of galaxy formation and evolution, suggesting that these cosmic giants may influence the universe in ways we have yet to fully comprehend. As new instruments capable of detecting gravitational waves with greater sensitivity come online, scientists hope to capture direct evidence of supermassive black holes merging, an achievement that would open an entirely new chapter in our understanding of the cosmos. Now turning to the next enigma, we explore the baffling imbalance of matter and antimatter in the universe, a puzzle that strikes at the very foundation of physics. As the next challenge unfolds, we dive into one of the most perplexing enigmas in modern physics, the missing antimatter in the universe. According to the best scientific models, the Big Bang should have produced equal amounts of matter and antimatter, two opposites that annihilate each other upon contact, leaving behind only energy. If this were the case, how do we find ourselves in a universe dominated by matter, with antimatter seemingly absent on a grand scale? This imbalance sits at the very heart of one of physics' greatest mysteries, challenging our understanding of how the cosmos came to be. Scientists have been searching for answers through a variety of experiments designed to study the subtle differences between matter and antimatter. One key focus has been the behavior of particles like protons and their antiparticles, antiprotons, looking for slight asymmetries that could explain why matter came to outweigh antimatter. These differences, though exceptionally small, could hold the clues to why our universe managed to escape total annihilation in its earliest moments. The Large Hadron Collider, the world's most powerful particle accelerator, has played a significant role in exploring these questions. By smashing particles together at near light speeds, it allows physicists to recreate conditions similar to those of the early universe. Early findings have revealed intriguing hints of asymmetry, known as charge parity violations, which may help tip the scales in favor of matter. Another avenue of investigation has been searching for traces of antimatter in space itself. Instruments aboard space telescopes, such as the Alpha Magnetic Spectrometer, have scanned the cosmos for signs of antimatter nuclei. While these efforts have yet to uncover definitive evidence of large concentrations of antimatter, they have deepened our understanding of cosmic rays and the particles that fill our universe. Theories attempting to solve this riddle range from the idea that antimatter and matter were separated into different regions of the universe during the Big Bang to the possibility that unknown forces or particles influenced the survival of matter. Some even suggest that tiny black holes formed in the early universe may have played a role in consuming antimatter more efficiently than matter. Yet, despite these efforts, the missing antimatter remains a profound puzzle. The resolution of this enigma has the potential to reshape our fundamental understanding of physics, unlocking new insights into how the universe formed and why it exists in its current state. And as scientists continue to unravel this mystery, we turn our attention to another colossal question: the vast and mysterious region known as the Great Void, a phenomenon that challenges the fabric of the universe itself. Moving forward, we encounter the Great Void, one of the most staggering and mystifying features of our universe. This immense underdense region stretches across hundreds of millions of light years, containing significantly fewer galaxies than expected based on our understanding of cosmic structures. To picture its scale, imagine a vast emptiness spanning distances so great they defy human comprehension. A void so large it dwarfs even superclusters of galaxies. But why does such a massive void exist, and how did it form? These questions continue to perplex astronomers as the existence of the Great Void challenges the current models of galaxy formation and the distribution of matter in the universe. According to the standard model of cosmology, matter should be relatively evenly distributed on the largest scales, with galaxies and clusters forming in dense regions while emptier patches like voids are much smaller and less dramatic. Yet the Great Void breaks this mold, presenting a level of emptiness that is far beyond what theories had predicted. Some researchers suggest that this colossal void may have emerged due to the random distribution of matter during the early stages of the universe, a leftover relic of quantum fluctuations shortly after the Big Bang. Others propose that it could be influenced by mysterious forces like dark energy, which dominates the universe and drives its expansion. Dark energy may have played a role in pushing matter away, intensifying the emptiness of this region. The implications of the Great Void extend beyond its sheer size and emptiness. Studying it provides valuable insights into the role of voids in shaping the large-scale structure of the universe. Voids are not merely empty spaces, they play an active part in the cosmic web, the vast network of filaments and nodes formed by galaxies and galaxy clusters connected across the universe. These structures interact with one another gravitationally, and voids like the Great Void help define the boundaries and behavior of these intergalactic connections. Additionally, the Great Void might serve as a unique testbed for cosmological theories, including the elusive properties of dark energy and the potential existence of other cosmic anomalies. Could such voids hint at processes or phenomena we have yet to uncover? The answers may lie in future observations with more advanced telescopes and simulations that push the boundaries of our understanding. As we grapple with the challenges posed by the Great Void, our journey takes us to the very edge of what we can observe, diving into the mysteries that lie at the limits of our cosmic vision. With the next phase of the journey in sight, we arrive at the edge of the observable universe, a boundary that represents the farthest distance we can see, limited by the age of the universe and the speed of light. This horizon, marked by the glow of the cosmic microwave background radiation, serves as a window into the infancy of the cosmos, offering a glimpse of the universe as it existed nearly 14 billion years ago. But what lies beyond this observable edge? The truth is, no one knows for certain, and this question pushes the very limits of human understanding. Some scientists speculate that beyond what we can see, the universe may stretch infinitely, containing countless galaxies and structures that remain hidden from our view simply because their light has not yet had time to reach us. Others suggest that the universe might not be infinite at all, but rather curve back on itself in ways that defy our intuitive understanding of space. Beyond these possibilities lies another tantalizing theory, the multiverse. This concept proposes that our universe may be just one among countless others, each with its own laws of physics, dimensions, and possibilities. If true, it would mean that our observable universe is but a tiny bubble in an unimaginably vast and diverse cosmic ocean. The idea of the multiverse, though fascinating, is challenging to prove, as evidence of other universes lies beyond the reach of current technology and observation. Adding to the enigma are the limitations of light travel itself. Light from distant regions takes billions of years to reach us, carrying information about the universe's past but concealing its present state. This means that even as we peer into the depths of space, we are not seeing the universe as it is now, but as it was long ago. The sheer scale and age of the cosmos make it likely that regions far beyond the observable edge have already evolved in ways we cannot begin to fathom. The edge of the observable universe is more than just a physical boundary. It challenges the very way we think about existence. It fuels debates about the nature of reality, the possibility of infinite space, and the fate of the cosmos. What lies beyond this edge may hold answers to the deepest questions of science and philosophy, or it may forever remain a mystery beyond human reach. As we stand on the precipice of the known, the unknown beckons us to continue exploring, pushing the boundaries of our imagination and technology. Our journey through space's most baffling phenomena ends here, but the quest for understanding is infinite, just like the cosmos itself. As the sun rises on the next chapter, we pause to reflect on the 30 phenomena that have carried us through the depths of space, each more mysterious and awe-inspiring than the last. From the enigmatic pull of the Great Attractor to the unrepeatable wow signal, from rogue planets wandering the cosmos to the tantalizing idea of the multiverse, these cosmic riddles reveal just how little we truly know about the universe we call home. Each discovery pushes the boundaries of human understanding, challenging the frameworks of science and inspiring new theories that aim to bring us closer to the truth. Yet, for every answer we uncover, countless more questions emerge, reminding us that the universe is not just a realm of matter and energy, but a boundless source of wonder. This endless mystery is what makes the cosmos so captivating, drawing us to gaze into the night sky with curiosity that knows no limits. Which of these phenomena sparked your imagination the most, and what are your theories about the secrets of deep space? Share your thoughts in the comments below, and if this journey through the universe left you inspired, don't forget to like this video, subscribe to the channel, and turn on the notification bell to join us for more explorations into the unknown. Until next time, keep looking up and pondering the infinite universe beyond.